Welcome to my presentation taking place in highly unusual times. So I tried to adapt, and I'm going to talk about how photons may come to the rescue in these difficult corona times. I'm going to talk about photonics for rapid and highly sensitive disease detection. Let me start with a sentiment that you all know. A little sneeze and you're worried. What's wrong with me? Is it just a common cold? Or is it the beginning of a COVID infection? So what we would all like to have is a fast, reliable, and affordable medical diagnostic system. Something like that. Lab on a chip on your keyring. So the grand challenge is low cost, reliable, fast, and sample preparation-free biochemical analysis of any of your body fluids. Now, as a photonics researcher, you may have the idea, hey, this is simple. We have a solution. Spectroscopy is what we need to do. And this example here is the mid-infrared spectrum of vanillin. And the spectroscopist don't even have to smell vanillin. Just looking at the spectrum, he will have the feeling, oh, I smell vanillin. Now, it's not as simple as that, because your body is a complex machine. Let me illustrate this with a complex slide. On the horizontal axis, I show you some of the proteins that can be found in your body fluids. If you believe that, oh, these are a lot, no, it's not dozens. It's actually thousands and thousands of different proteins that can be found in your body fluids, for example, in your blood. On the vertical axis, it's the concentration these different analytes have in blood. And that's my point. You see that? It's 12 orders of magnitude in concentration. So let's be honest. Biochemical measurements are really difficult. And to bring this message home, I have an illustration for you. And I'm using the Where's Waldo Now picture book to show you which 4 criteria must be met so that you can really do reliable biochemical measurements. So first thing, you know the picture books. So you have to find Waldo. There are many different people around. So where is Waldo? What you need is high sensitivity in your detection. High sensitivity. But that's not all. If you have the feeling, oh, here it is, the object I need to detect, no, you got it wrong. It's almost the object. So in this case, it is Wenda, the girlfriend of Waldo. So it's not good enough to find an object, an analyte that is close. It must be exactly the analyte you're looking for. So you need high selectivity. That's not all, because just looking for one analyte is often not enough. What you need is a complete panel of analytes. So what you would like to get is simultaneous measurements of different analytes. And there's a last thing. If your measurement is not stable, no chance. You can't do a reliable measurement. You won't get a reliable result. So the last demand is you need stability in your measurement. In summary, if you really want to do biochemical measurements, you need a method that is sensitive, because you need to measure minute concentrations of biomolecules present in with a large dynamic range. You need to be highly selective because you need to be sure, is this really the molecule I wanted to detect or just one that looks similar? Then you want to be fast and simultaneous because you want to measure a complete analyte panel. And finally, if your measurements aren't rock solid and really stable, you can't be sure what you're measuring. Now, I haven't talked about photonics. Why does photonics come into play here for biomedical measurements? And it becomes clear if you look at the taxonomy of biosensing measurements. I have tried to list here different measurement techniques that are all being used for biosensing. And you immediately see, yes, there are non-optical methods, but there are more optical methods than non-optical methods. Let me show you how such a typical optical photonic measurement system works. So on a surface, you have immobilized receptors, the Y-shaped molecules. If you have an analyte which you would like to detect, the squares, when these analytes come close to the receptors, they bind. So they change the surface slightly. What this means is that we are highly selective because we've used chemistry. It's not only photonics, this is a technology teamwork. So chemical transduction allows to reach high selectivity. But now, what is the sensing mechanism? Well, these combinations of Y-shaped receptors and analytes, they change the refractive index of the surface slightly. So what you can do is you can use interferometric techniques to measure how much has the refractive index changed, and therefore how many bound analytes do you have on your surface. So you see, it's chemistry for the selectivity, it's optics or photonics for the sensitivity. Now, what about the stability and simultaneous measurement? This is given through miniaturization of the whole system. Because if it's small, it's much easier to keep stable. And if it's small, it's much easier to have an array of such measurements. Let me show you a typical example of a measurement system, how it's used today in the lab. In this example, it's a grating-coupled waveguide approach. And the measurement system itself is, tabletop sized. But the measurement is taking place on a very small cartridge, a few centimeters. And the action is on a few square millimeters where we've got a functionalized surface. Now you might ask, why do we need such a big tabletop system? Well, it's a lot of chemical reservoirs, of waste reservoir. You have temperature stabilization method, you need pumps, you need the different optical elements for emitting light, very stably so, for detecting light, very stably so. So the infrastructure is enormous, while the actual measurement is taking place on a very small spot. Now, to end, I have a take-home message for you. If you want to make biosensing measurements, that's a hard task. So select your partners wisely. Select partners who are 4S proof. Partners like HAMAMATSU, because photon is our business. So thank you very much and stay safe.